Welcome. We're going to be looking at the coefficient of friction in the following video. So we've already talked about friction, and we want to know first, like, what is friction and what causes it? And so in this case then, let's take a block that's sliding across a tabletop. So as I push this, the block is going to slide. And we know that friction is going to go opposite the way it is sliding, which we would call kinetic friction. So in this case, since it's sliding to the right, the kinetic friction is going to point opposite that to the left. We also know that for static friction, it would be opposite the way it would slide, since it's not actually sliding. So more formally then, friction is going to represent the force that's between two objects' surfaces, in this case the bottom of the wood block and the top of the tabletop. It always acts along the surface. Since it's a force between the block and the table, both the block and the table will feel a force of friction, and those are going to be equal and opposite, as we'll look at here in a moment. As we said before, friction is always going to point against the way the object is sliding, if it's sliding where it's touching the surface, or opposite the way it would slide with respect to the surface if it would slide if it were super slippery. So let's take a look at that between two objects idea. So I have a leprechaun sitting on a wood block. And the idea would be as I pull this block, you see that the leprechaun falls off the back. So we're going to assume that he's sliding off the back end of the wood block. And what we're going to try and do is draw an arrow representing the force of friction acting on the leprechaun as it slides. So I'm going to focus in on the two objects we have here, the leprechaun and the wood block. Let's focus on just the leprechaun. So that point of contact is with the leprechaun's bottom and the wood block. Now if it slides to the left on top of that wood block, then notice here we're going to have a frictional force that's going to go opposite the way it slides. Let's rewind it. So again, it's going to go sliding to the left, which means friction is going to point opposite the way it's sliding. And then he falls off. We can also focus instead on the leprechaun, which we know has a frictional force to the right. We can also focus in on the wood block because that's the other surface that is experiencing friction. So if we draw an arrow representing the force on the block from the leprechaun, then it should be pointing the opposite way from what we just had. So the leprechaun experiences a force to the right, the block should experience a force to the left, just based on Newton's third law, which is the equal and opposite force between objects. But let's double check due to the sliding. So if we look at the block, which way is the block sliding with respect to the leprechaun? The block's going to slide to the right. And that means that the frictional force is going to go opposite that to the left. So let's rewind. As the block moves to the right, frictional force is to the left. We'll typically only look at one of these two objects, but this is to just convey the idea that friction acts between the two surfaces that are interacting and is exerted on both surfaces, although we'll probably just look at the one on top, like the leprechaun, for example. If we look at how to measure this, we did some work with measuring friction already in class, but since we have two types of friction, we want to be able to measure those two types of friction as well. So first off, we're going to be looking at static friction. Now, static friction is going to represent any force of friction needed to keep it stationary. So as I push on this, notice that it's not going to move because friction is balancing out my push. And then I'm going to keep pushing until I can get to budge, and then I'm going to lay off. Like right there, it budged. Okay, I'm going to keep pushing, see if I can get it to budge again. And you can see it's not budging, and then all of a sudden it budges, right? And so in that case, friction static was matching my push. And as I increased it, kept matching my push, but then I broke it right there, and it caused it to budge. So that represents the maximum the static friction was willing to do. I repeated that and noticed it's about the same point each time if I'm careful and push with just enough to get it to budge. So what happens if I wanted to measure kinetic friction? Obviously, we want to let it slide. So I'm going to go ahead and push this at a constant speed. So I'm going to get it to budge, and then I'm going to push it with a constant speed. And if I push with a constant speed, my push should be balanced with friction and create a flat line. And I can average that flat line to get the force of kinetic friction while it was sliding at a constant speed. So in summary, I can measure the maximum force of static friction by measuring that peak value. The force of static friction can be any value it needs to be up until that maximum value. I can also measure the force of kinetic friction by just pushing it at a constant speed and getting the average force of friction while it's sliding at a constant speed. This is a graph that you might see on websites and textbooks and resources. It's very common. And so what we're looking at here is the same, this is a real graph that I made. This would be what it would be ideally. So the idea is that static friction is going to be, if I have 1 Newton of push, it's going to be 1 Newton. If I have 2 Newtons of push, it's going to be 2 Newtons. If I have 3 Newtons of push, it's going to be 3 Newtons. And it's going to go all the way up until I break it where it budges. That represents the maximum force of static friction. From there, it's sliding. And so the frictional force would be constant and represent kinetic friction. So what causes friction? I understand how to measure it and I know what it is. But force of friction depends on the amount of force that's pushing between the two objects. So if I have two objects where the surfaces are laying on top of each other, how much force is pushing between those? And you may say it's the object's force of gravity or weight, but really that's going to be balanced with normal force if it's just a block sitting on a surface. If I push something that's sliding along a wall, then it wouldn't matter about the weight of it. It would matter how much I'm pushing that block into the wall. So normal force being the surface force that pushes perpendicular away, that will always be present when you have contact with a surface. So we're going to use normal force to represent how hard those forces push into each other. And then the other thing would be the texture of the surface, how rough it is. And that would be between the two objects, so both objects matter there. So if you think about it, then when we have some block on a surface like this, and I were to zoom in on that, like down to the microscopic level, even smooth surfaces are going to look bumpy, right? And it's this interlocking and interaction between the bumpiness of the two surfaces that generate the friction that we can measure. So ultimately, we want to be able to quantify surface roughness. I want to be able to put it into an equation. So I can't just be like, oh, how rough is that surface? And you would be like, I give it an 8. It's pretty rough, or it's pretty smooth. Probably a 2, right? We have to come up with a more scientific way to measure a value. We can't just estimate it. So that value, that rating that I was using an example of like a 10 scale, that's actually referred to as the coefficient of static friction. We just want to get rid of the opinion aspect of it. And so how do we want to get that value? How do we obtain it? If we don't want to just estimate it, what equation can we use to predict how rough that surface is if it were on a 10 scale, for example? So this coefficient of friction is going to measure how well the two surfaces are at producing force of friction. And we can't just use the force of friction for surface roughness, right? Because the normal force also affects that force of friction. So we can't just say, oh, there's a lot of force friction, because I can cause that to change situation to situation by putting more normal force in or less. So I need to divide out how much normal force there is. So what I'm looking for is how much friction there is, like how many newtons of friction there are per newton of normal force. That way the normal force is sort of removed from the equation. If you need to see the math for this, what I'd be doing is saying, let's take the force of friction and divide it by how much normal force that is, and that ratio should give us a rating for how rough the surface is. If for 1 Newton of normal force, some rough surface can generate more friction, then that means it's a rougher surface. So if we write this in a general form with the actual variable we would have then this Greek letter mu, which looks like a curvy U. Again, that's the Greek letter mu that represents this coefficient of friction. The coefficient you could think of as the rating of friction. So coefficient of friction is the surface roughness. And if we use that peak value of friction's static, meaning called the max force of friction static, then we would get the static coefficient of friction. If we use kinetic friction, since it's different, then we would get the static coefficient of friction. If we did it for a bunch of different normal forces, so let's say we stacked weights onto some object to change the normal force, then you could see here, for example, if we follow the blue one is going to be static friction. So if we had this many newtons of normal force, we had this many newtons of friction. And as I increased and doubled the amount of normal force, I was able to increase friction, but that ratio would remain fixed. And it's that ratio that is the coefficient of friction. So that would mean for this graph of normal force versus friction, it would be slope, which makes sense because sloping rise over run, if I plotted friction, the maximum force friction, sorry, over normal force, I would have mu, which graphically would be the maximum force of static friction over normal force. And so that means the equations that we could use from here if we were going to do algebra problems would be these equations, which would appear on the top of your worksheets and problem sets, quizzes, and tests. And we can use this now as an extra equation with which to solve force problems. Thank you for watching.